Hey all, let's talk a little bit about graphs real quick because it's really important that you, not just for science and this class, but in general, have the capability to read and interpret graphs. A graph is just a visual interpretation of data. And a good graph can make or break the story that is being told by the data. Unfortunately, Um, you can also manipulate data in a graph to tell the story that you want it to. But if you follow very specific rules on how to make graphs, then you can avoid most of those. Um, in this short little video, I'm going to tell you about some of the main types of graphs we use and the basic components of a graph. And then we're going to watch a short video on how to spot a misleading graph because these are everywhere. And it's really easy to make a graph that is misleading simply by not knowing exactly how to make a good graph. But also, if you know how to make a good graph, you know how to make a very good misleading graph. So let's go ahead and get started. So on this Excel file here, I've got several graphs. I'm going to work through several different sheets, so bear with me. But this first one here, this is what we call a line graph. But before we talk about the data in the graph, let's talk about the components of the graph. So we have an x-axis. This is our x-axis here, the horizontal axis. And then here is our y-axis, the vertical axis. In graph making, we put our independent variable along the x-axis, and we put our dependent variable along the y-axis. That is best practice. Um, in this case, our independent or experimental variable is time in minutes. And notice that I have the name of the variable as well as the units. Including units is very important because if this was seconds or hours or years and you didn't have the indication there, then you would have no idea how quickly this reaction occurred. So having the units is crucial. Similarly, on the y-axis, we have our dependent or response variable, product formed, and in this case, milligrams. This is just a generic data set, so there's not really much information presented here. But in any case, you want to have a descriptive title. And if you don't have a title, you have a descriptive caption, which will go below the chart. In this case, we just have a title. And the title is Amount of Product Formed After 10 Minutes. Nice and descriptive. You really don't have to do much digging to figure out what this graph is depicting. I tend to leave out grid lines because grid lines can clutter the look of the graph, but that's kind of a aesthetic choice. You'll see different papers and different journals using different styles. That's just the style I like. And in this particular graph, a line graph, we have time along the x-axis, which is a very common usage of the line graph. If you have a data set that includes time, you're almost always going to have some sort of line graph, okay? So we put time along our x-axis, and notice that the units, the interval between the units, I should say, is equal. You wouldn't go 0 to 2 to 6 to 12 to 24. That would not make sense, especially in this case. There are cases where you have a different sort of scale, like a logarithmic scale, which is basically what I just described. But most of the time, we want this to just be a linear scale, just like the number line, where the distance or the number of units between each tick mark, if you will, is equal. So there's 2 units between each mark, right? Same thing on the y-axis. In this case, we only have 1 unit between each tick mark. 1, 2, 3, 4, 5, 6. To plot this data, we go up to our little data table here, and we notice that at 0 minutes, that's right here, the amount of product formed was 0.2. So we would go over to 0 and up 0.2 to arrive at that point there. 2, 2.57, so 2, up to 2.57, right? 4, 4.77, 4, 4.77, and so on and so forth until you've filled out this whole graph. And since it's a line graph, you connect those points to get this curve. So line graphs are really useful when you're trying to display time series data. You're trying to see how, in this case, how the amount of product changes over time. This is most likely some sort of enzymatic reaction. So enzymes breaking down or producing some product, some other protein or whatever it might be. Whereas the second graph on the right here, this is called a scatter plot. This is where we have two different types of data that one is not time series in this case, and we're trying to determine if there is a correlation between those two types of data. So in this case, we're looking at the relationship between the size of a pill and the contents of that pill. So we've taken the length of these pills in millimeters, right? And then we've measured the amount of calcium carbonate that is in them. So this is probably something like a Tums or something. Amount of calcium carbonate in milligrams. And if you look at this graph, you can see that if you connected the dots, which is not what you want to do in a scatter plot, but if you did, you would get this kind of bouncy line. And that doesn't really tell us anything. Think for a second. Pause this video and be like, okay, if I connected the lines, the dots here, would this tell me anything about the relationship between pill size and contents? Not really. But if you imagined a line, a straight line, between these points that minimize the distance from each point to that line will be something of a straight line that's almost horizontal, right through here. It wouldn't be a line like this. It would not be a line like this. It would be almost straight through there. And we add trend line. That's what we're looking for. And you'll see that this line basically flat right through all those points. And what that tells us is that there is no relationship between the length of a pill and the amount of calcium carbonate in it. In other data sets, you'll get a trend line that is either increasing or decreasing. If you have a trend line that goes up, you know that there is a positive correlation. If the trend line goes down, it's what we call a negative correlation. So let's look at some different line graphs and what positive correlation looks like. In these graphs, I've taken various different body measurements of some different lizard species and compared it to their sprint speed. So in this top left, we have hind limb length versus sprint speed. This one has snout vent, which is a way we measure the length of a lizard. It's basically the length of the lizard minus its tail, whereas here is just the tail length. This is the tail length versus the sprint speed. As you can see, in all of these graphs, these are all scatter plots, and we can remove the trend line if we wanted, but we would still see that as the hind limb length increases, for example, that the sprint speed also increases. That is a positive correlation. And we actually see this in all of these different variables, but it is the strongest here in hind limb length, which probably makes sense. Lizards with longer hind limbs are going to be faster, similar to how humans work, right? Longer legs, you're typically faster. So that's a positive correlation. If you flip this and had a line that was going down, you would know that as hind limb length increases, sprint speed decreases. That's obviously not what we see here, but that would be a negative correlation. Okay, let's move on. Go back to this one. Let's go here. So this is called a bar graph, but it's actually a special type of bar graph. It's a histogram. So a bar graph is obviously typified by these big bars. That's an easy way to identify a bar graph. A histogram you can identify quickly by noting the y-axis. The y-axis is going to be frequency or count data, the number of times something occurs. So this particular data set is age groups, and the number of people within each of these age groups that comes to the ER on a Saturday night. I know, very specific data set. So, patients that were under 20 years of age, there were 4 of them. Patients between the ages of 20 and 30, 7. Patients between the ages of 30 and 40, 1. Patients between the age of 40 and 50, 8. So on and so forth. I would expect the numbers here to be the highest, but kind of not what we see. Yeah, interesting. In any case, a histogram is a special type of bar graph where we plot data according to the number of times that it occurs. So our independent variable is the age, whereas the dependent is the frequency, the number of times that that data point occurs. Let's now look at a different type of bar graph. This is a more stereotypical bar graph. This is not a histogram. This particular data set is looking at the survival of larval amphibians, specifically spotted salamanders and wood frogs, in roadside ponds. These salamanders and frogs live in a part of the country where they often have to salt roads to make sure the snow and ice doesn't freeze on the road, making the road really treacherous. And this salt often runs off into these ponds and makes the water very salty. Conductivity here is a measure of how salty a solution is. The more salty it is, the higher the conductivity. Okay, so spotted salamanders are the orange bars, wood frogs are the gray bars. You can see here our excuse me, independent variable is conductivity, and when there is 0 conductivity, that means this is like purely fresh water. Larval survival, percentage of larval amphibians surviving to adulthood, is very high. 80 to 90%. 91% for the wood frogs, 84% for the spotted salamanders. You bump that conductivity up 500, you get 68% survival for the spotted salamanders and 77 for the wood frogs. It's already gone way down. And then at 3,000, spotted salamanders do very poorly. Almost none of them survive, and wood frogs are down to 41%. That's less than half the original survival percentage. Right? So this is a quick and easy way to say, oh, the higher the saltiness, the lower the survival, right? And that's really easy to see from this bar graph. Okay, let's go on to our final type of graph. So far we've covered line graphs, scatter plots, bar graphs, and this last one is not a very commonly used one, at least in biological research, just because there's typically better ways to represent it, but a pie chart. And pie charts are called pie charts because they look like slices of pie, right? In this particular pie chart, I've taken the numbers of species in different vertebrate classes. So we have fish, mammals, birds, reptiles, and amphibians. Those are all the animals that we consider vertebrates. By far, the most of the vertebrates are fish. Almost 33,000 species of fish. The smallest class of vertebrates is mammals, with only 5,513. Birds and reptiles, similar numbers, and amphibians lagging behind just a little bit. So this is another way, because this is parts of a whole, right? If you're trying to show parts of a whole, pie chart is a great way to go. But other than that, pie charts are not commonly used in biological sorts of utilities. They're a little better for financial type stuff, which is when you mostly see them.